Well, welcome everyone. I'm going to get started. So first of all, thank you so much for attending today's webinar. Um, Before I kind of introduce myself, I'm going to kind of kick off a poll. So if you have some time, just work on that poll, just a couple questions. Great, so happy to be here. My name is Drew Buchanan. I'm the engineering manager here at True Insight. And if you're unfamiliar with True Insight, we are the channel partner for Altair. I'm going to be running through today three tools that sometimes can be often overlooked within the Altair portfolio, which are MotionSolve, HyperStudy, and Multiscale Designer. So I guess a few things first. If you're unfamiliar with Altair, Altair is a high-end simulation and design company. They leverage a lot of different solutions, really, for all you guys who are designers and engineers to kind of make informed decisions, whether it's focusing in on simulation or HPC or even AI. And the focus of today, we're kind of talking about three different tools. Some of them are physics-based, others are more automation-based, and some are actually material development. The broad picture, due to Altair's licensing model, there's a lot of different solutions that customers and users have at their fingertips. So in this case, if you have any questions about anything, maybe pertaining to what I'm talking about, my colleague is in the chat. He's able to answer questions, and I will save some time at the end to go over some questions as well. But if you also have maybe something that doesn't pertain directly to what we're talking about today, let us know in the chat. We probably have some type of solution out there for you. So great. So what's today's agenda? We're focusing on three different tools, specifically MotionSolve, HyperStudy, and Multiscale. More often than not, a lot of these tools are used in conjunction if you have some type of multiple engineering teams at your company. So I figured it'd be kind of some good exposure to talk about how you can utilize these tools. You may have some use for them, but maybe someone else on your engineering design team could also have some use for them. And like I said, we'll save some time at the end for some questions. So let's talk about what exactly is MotionSolve. So MotionSolve is a multi-body simulation solver. Pretty much it's simulating the mechanical motion of systems. And these motions can be caused by forces or restraints or couplings. You kind of see this bulldozer right here that's moving around. This would be a classic example of something you'd solve in MotionSolve. One of the key things that you're really doing is you're trying to determine what's happening with the required motion. So if you're trying to actually design the hydraulics and how much force is going to lift the system, you can use MotionSolve to do that. Another common application is maybe you're building out motors and you need to see how much torque will kind of be generated, and will it actually kind of move my vehicle or move my device. Lastly, the solver itself, MotionSolve, is the Altair specific multi-body solver. It's integrated in interfaces across Inspire Motion and also HyperWorks. What I'll be showing today is just within HyperWorks. If you do have questions on Inspire Motion, I can kind of answer them at the end. The key thing is with the MotionSolve solver within Inspire Motion is kind of a reduced version of the full MotionSolve solver enabled in HyperWorks. So specifically, one of the cool things about multi-body simulation, if you're not familiar with it, I'm guessing a lot of you probably are familiar with FEA. They're kind of in the same family. Both of them are based on the mechanics of principles of mechanics, the equation of motion. The key difference is multi-body simulation focus on the macroscopic behavior of the system. You kind of see on the left a large car. You're simulating what's happening as it's kind of moving in between those lanes. You're not necessarily focused on the really, when I say microscopic, the internal parts, how they're, causing stresses and displacements, whereas FEA is more concerned about the microscopic behavior of a system, how something is internally deflecting. With that being said, MotionSolve can handle flexible bodies. We can do some, internal deflection, but it's generally looking at large time events that are dynamic, and you're looking at a large system. With that being said, multi-body simulation tends to be very efficient for larger systems. You're not solving as many equations. So it's a really good understanding of what's happening to something dynamically. Bear in mind, in FEA, you can do some dynamic analysis. You know, you might be thinking of explicit or crash testing, but those analyses, they typically are microseconds or milliseconds. You can't capture things for a long event of time, otherwise you're gonna have a huge model. So there's reasons why you might use one or the other. So specifically, if you've never used kinematic simulation, I'm sure probably, you know, some of you might be familiar with this equation. We know through mechanics, everything has a capability. If you're sitting at your desk right now, you can touch an object, you can move it translationally, you know, in the X, Y, Z directions in those three axes, or you can rotate something, which would be across the X, Y, and Z. In MotionSolve terms or multi-body terms, that's known as the degree of freedom. Actually, in FEA terms, we kind of refer to nodes as well of degrees of freedom. So how we govern how MotionSolve works is we restrict motion via either, you know, a specific force or motor, or we restrict via joints. Joints are very similar to how if you've worked in CAD systems before, how CAD mates work. They restrain what's happening in systems. So we see on this image on the screen right here. Here's a classic example of MotionSolve. We're restraining the motion in the Y direction. Obviously, it's a really simple example right here, but it cannot rotate. It can only move axially, so it only has 1 degree of freedom. So we could actually simulate this in MotionSolve, and now we could look at the frictional forces. You know, how much force is it going to be able to push that piece of wood through that channel? So there's a lot of kind of applications there. So I figured since we're talking about joints, one of the other things to kind of keep in mind is that joints are going to be what's restraining the system. So that's an equilibrium. So this equation right here is known as Grubler's equation. Generally, you want to make sure you're in equilibrium. You're not removing more degrees of freedom in your system than you currently have. And these are the types of joints you have. So you see, joints are how two parts interact with one another in MotionSolve. And you'll see that as we kind of go through it through our example, it's how we kind of restrict motion either translationally or rotationally. One of the really cool things about MotionSolve, though, is it has compliant joints. Compliant joints really are, you think about them as bushings. Bushings allow some relative motion in 6 degrees of freedom. So if you have something that maybe is over-constrained or under-constrained, you can use a compliant joint, and that's actually going to allow the system to solve. Some other motion tools out there, you have to spend a lot of time making sure all your joints are set up properly. MotionSolve kind of alleviates that by using compliant joints. All right, so let's jump into an example. So I'm going to minimize my screen here, and let's jump into MotionSolve. So one of the cool things about MotionSolve, it's directly integrated into HyperWorks. If you've never seen HyperWorks before, it's our large platform for structural, in this case, kinematics or motion, but also CFD. And it also has the pre and the post. So you can do meshing here. You can also look at individual results, but in this case, we're actually running a kinematic analysis. The first thing, we can import our CAD model. So there's a variety of things we can bring in. So in this case, everything we'd want. You can characterize motion for a simple part, but more often than not, when I see users utilizing MotionSolve, it's for assemblies. So in this case, we actually have an actual pulley right here and a gear. And we're gonna specify a motion based around the rotation of the small pink gear right here, the pinion gear. And you'll see in my system right here, how everything is set up in MotionSolve is based around the specific rigid body dynamic boundary conditions right here. So we specify our joints, our motions, our forces, or even, you know, springs or bushings, we can apply them. In this case, we actually have a motor that's being applied, and the motor you see right here is this pinion right here. And you'll see that I'm actually specifying about a 75 degrees, so this is in radians, 75-degree rotation here. So it's going to move a little bit, and we'll run 2 different cases where we're adjusting it, where we go from 1.3 to, you know, maybe increase it a little bit more. A couple other things to keep in mind. One of the cool things about this tree is it kind of sorts everything where you're at. There's a lot of power behind this tool. I mean, I can generate lots of custom outputs, you know, in terms of how I'm setting up my model. There's so many different types of requests that you have at your disposal. And if you're doing, you know, any type of motor design, or you're really trying to size things out, you know, building cams, this is invaluable because everywhere in the system, I can look at what's happening to the individual component. You'll also see there's motion contact right here. So you see these two parts are highlighted. You'll see that I can specify within this specific value what its contact properties are. So, you know, in reality, you're sitting at your desk right now. You move a part, there's probably some frictional coefficient being applied. If you have two parts, you know, if you drop your phone or something on the desk, there's some type of impact stiffness. We can key all these values in accordingly. So in this case, I don't have friction force applied, but I do have some impact stiffness values applied for each of these motion contacts. Note by default, based on kind of default mechanical properties, MotionSolve can kind of calculate these automatically for you, but you can also adjust these. Okay, great. So let's actually solve this system. We'll solve it in real time. So what you'll see is you're going to see the actual dynamic motion as it starts to solve. It's writing to my directory, and it's going to do this reasonably quick, you know, in about a minute or two in terms of what I've timed out. But it's a great way of kind of going through and calculating what's happening to the system. One of the other things to kind of keep in mind when we're looking at these types of results, you kind of see right there, it showed the animation and finished out. Like I said, a couple of minutes. So if you were trying to do this in FEA, you know, you'd have to run, you know, you could try and solve this in implicit FEA. That would be super difficult with all the contacts. Maybe explicit might be able to handle it, but again, it's going to be something that takes way longer, and because there's more equations to solve. So I think that's really where the power of using a kinematic-based solver is. And note, you can apply some tools that aren't rigid. You can actually apply what are known as flexible bodies, so there is some deformation allowed. So it's a good way, if you've never utilized this approach, if you're dealing with a large system that has dynamic loading, to kind of approach this. So we saw the animation right here. You can actually animate it more and adjust frame rates in Hyper-V and save out animations. But what's also, you know, what's kind of, you know, the other kind of key thing, what users are utilizing MotionSolve for is specifically obtaining results, whether it's displacement, velocities, accelerations, or torques. Let's actually go to plot. So plot is actually going to load a new screen on here. It's actually one of our post processors. It's called Hypergraph. It gives you the capability to kind of post process our results. So if I hit open here and I go to this motion model I just ran, ABF is the hypergraph file. So if I hit open there, you'll see all the different values I have at my disposal. And these are all those kind of requests I built. You can also kind of create custom mathematical expressions. So like I said, like there's a lot of power under the hood here. If I go to, let's go to one of these joints. And remember, the joints are how the two parts interact. So joint 14 was that joint I just pointed out to you earlier. If we go there and look at the displacement and then hit plot, you'll see what's happening to the displacement. And that makes sense because you'll kind of see as we watch the animation, the pulley goes in and out. So it's a good kind of representation of what's happening to the system. Excuse me. One of the other cool things about this is that you'll see this gets put on another page. I can go back to my first page where the MotionSolve study is, and I can iterate. And that's kind of the other power of this. If you're kind of trying to do this on the shop, you're going to spend a lot of time. And I can go real easily right here and maybe just adjust how much this motor is going to rotate at. So if I go to 1.5 radians, and then if I resolve this, another kind of key thing to keep in mind, I didn't show the analysis settings, but you can specify the analysis settings here, what your end time is going to be. So you can actually kind of control the dynamics as well within the system. All right, so let's animate this now, or I'm sorry, let's solve this. So I'm solving for the new system. And again, it's probably going to take about a minute or two, but again, it's much more reduced in the system. And the other really cool thing about the solver is it has capabilities of leveraging more cores. You know, some other kinematic solvers are not set up to take advantage of multiple cores. MotionSolve is able to do that. You know, if you have enough units within your system, you can solve more cores. So again, that's why we have a lot of automotive customers utilizing this, because they can look at, you know, kind of large full systems. All right, so it just finished. You saw the animation. It rotated just slightly more. It's not significant, but I just wanted to kind of show you how you can kind of iterate and work through this. All right, so if I come here, I can bring up the newest ABF file. I see 145, so just what I just ran. And if I can come back here to joint 14 and hit plot, you'll see that we have our new displacement values. It's a little bit kind of steeper, but it's kind of still following that same profile, because again, I really didn't adjust the rotation that much. I didn't change the speed. I just specified it's going to rotate a couple more extra degrees. Okay, great. So let's hop back to my slides here. So we just started talking about MotionSolve. So let's talk about HyperStudy. HyperStudy really can be a powerful tool in terms of automating tasks. So specifically, if you've never used HyperStudy, HyperStudy is a multidisciplinary design software. What that means is it can take inputs from various sources. You kind of see in the image right there, we can take pretty much from every single Altair solver, you know, structural, but also electromagnetic, you know, FICO, flux motor, and then also OptiStruct and radios. The other really cool thing about this tool is it can actually utilize spreadsheets or parameterized scripts. You know, maybe they're not Altair files. And also we interface with some external solvers as well, like ANSYS and a few others. But one of the cool things about it is it allows engineers, you know, most of you probably are making, you know, design decisions on your designs, and we'll talk about it in the next slide, but there's a lot of decisions you guys have to make, and going through every single decision can be very kind of time consuming with kind of a serial based approach of going through simulation. With HyperStudy, you can kind of go through and automate all these tasks. The other really cool thing is HyperStudy has capabilities of utilizing kind of advanced analytics. There's a lot of data processing capabilities within it that give you the capability to kind of zone in on a lot of studies. So let's kind of take a look at an example. So this is an example. This is just a typical robot arm. And this is just to kind of get you guys thinking about, you know, where would you use a design exploration software? Where would you use HyperStudy? So if we look at this, there's so many different things that come into play. I mean, if you look at the dimensions, this is a somewhat complicated CAD part. There's numerous dimensions and changes, and all these are kind of controllable based off of manufacturing, you know, requirements. You know, how this part's going to be manufactured. There's certain tolerances, as probably all of you are aware of. The next thing is there's certain materials. You know, you're dealing with a certain distributor, or you're manufacturing, you kind of know the materials you want to utilize. And then lastly, there's some other parameters, you know, specifically, you know, maybe this part is being designed under certain temperature conditions, or there's certain surface finishes. There's so many different variables you can kind of input. When you kind of look at design, sometimes it can be an infinite, you know, infinite parameters of what's happening. Kind of that old term, you know, paralysis or design by paralysis. You know, if you're not kind of working, you can kind of get overconsumed. So where HyperStudy can kind of come into play is it can actually simulate a variety of scenarios. You know, generally we all have certain objectives and controls over our designs. All of you probably know what your limits are and your tolerances are, but it can be very time consuming to go through that. So HyperStudy can actually put all of those variables and permutations into one GUI. And then what it can do is it can then actually solve that scenario. Like I said, we're going to look at an example that's based around structural, but I want to keep in mind, if you're dealing with a lot of Excel data or, you know, just script data, you can use HyperStudy as well. So you're not limited by using, you know, some type of analysis simulation. We can also look at scripts or Excel data, and really it's great for kind of making design decisions for a large amount of scenarios or variables you have. So after you run the scenario, what HyperStudy will do is it will point out to you, what the actual results are based on the responses you specified. So kind of a classic example is I kind of might change my dimensional variables and I want to see what the max stress and the max displacement is going to be on the system. HyperStudy will deliver that, and then it gives you the capability of using its data analytics to kind of prove out which is the key contributing factor. So how HyperStudy works is it kind of has 5 different study approaches built into it. The cool thing about this is some of these are statistical based approaches and others are kind of more automated design based approaches. So DOE and BASIC, what it's doing, it's using a upper and lower bounds and then sweeping your results through scenarios within the GUI. So if you have like a dimensional variable, of an upper tolerance and a lower tolerance, you can feed that into HyperStudy, and then it can actually do that. And you don't actually have to go and change that kind of geometry. It's going to do that automatically, via the parameterized dimensions you specified in your preprocessor, which most simulation tools have that. OptiStruct and Radios have it. And then some of the others like Fit and Stochastic, what they'll do is they'll utilize some of the approaches you have, some of the models you'll run in HyperStudy, and then use statistical analysis to kind of extrapolate further out, where it kind of goes through a probability distribution. Based on what it's seeing, it can kind of tell you what's going to happen later. So you can actually do some really nice advanced analytics as well within the system. All right, so let's kind of take a look at an example here. So I have HyperStudy open here. Yep, here we go. So pretty nice system. We'll kind of step through this. Obviously, the model I have prepared, I ran a couple different cases. Didn't take too long to run, but for the sake of a webinar, I'm not going to run the exact scenario, but I'm going to kind of go through the setup so you can kind of see how it links with different tools. So if I go to new study here, if I specify where I want to save it, I'm going to put it into the, just a sample folder here. Okay. Yep, that's fine. And then what I can do is I can hit add model. And right here, you'll see all the different values I was kind of talking about. So like I said, HyperStudy works really well with all of our solvers. You'll see pretty much everything within our suite is here, but we also have some external capabilities here. Kind of see Workbench there and some external processors, and then also these parameterized files, internal math and spreadsheet. Like I said, it doesn't necessarily have to be simulation data. It could be large spreadsheet data you're trying to control and look at. So it's a very powerful tool. In this case, we're going to look at a hypermesh file. So I'm going to hit OK. So from here, we can specify what solver script I want to utilize. In this case, it's an OptiStruct file from HyperMesh. And then I can specify what file I want to bring in. So let me grab the file. All right. And then what I do, I'll just show kind of the starting process of this, is if I hit import variables, what it will do, it will automatically load HyperWorks. And then what it will do is actually load that model automatically for you. And how it works within HyperWorks is you just specify a variable. It's a parameterized variable. So in this case, it could be a dimensional variable. It could be, you'll see there's some material variables, and there could also be force variables. So in this case, I could specify all of my different kind of shape variables here, and all these pertain to just different values. I'm not going to hit OK here just because, like I said, it takes a few minutes for it to link all those variables. But again, it's a very nice streamlined process. So I'm going to hit cancel. That's fine. I'm going to go to my preloaded file so we can take a look at it. So what you'll see, what it brings in is it brings in these specific, all these specific variables, and we specify, our lower and upper bounds. This is what you have control over. In this case, it's -1 to 1, but you can kind of control what you want. And then what it does is you can test these models. It's going to kind of show you what your model data is going to be. And then from there, I can actually run a DOE, and you'll see in this case, there's like 61 different scenarios. It does this all within the tool. It delivers all the results and all the responses directly within the GUI. So if you're trying to do a lot of different kind of scenarios. As you know, it can become very tedious trying to do that in just HyperMesh or whatever sim tool you're working with. In this case, it kind of puts everything into the same environment, and then I can post-process very quickly. So when I look at post-processing here, there's a lot of capabilities, but I tend to like looking at a Pareto plot because it can kind of show me really quickly what all my responses, in this case, displacement and stress and volume. But one of the cool things is if you ever used Hyperview, we have an integration here where you can kind of set multiple different types of plots. So I'm actually going to create 4 different Pareto plots. And you'll see that everything's kind of pretty nice from the GUI. I can easily click on this. This is going to be max displacement. I can click here, select max stress. I can select maybe I want to go max stress 3 here. You'll see how it changes, and then our volume. So the individual max stresses are localized max stress variables based on faces. Max stress is the global max stress, and max displacement is the global max displacement. So in this case, we kind of see using this length 2.5 variable, it kind of contributes to the largest stress and displacement. So I would probably say, I would probably want to avoid this length for our system and probably go to maybe one of these other kind of dimensions here. We can see also from the summary, I have all those values, but there's also kind of see a distribution graph here. You can then start taking advantage of stochastics and maybe have a bunch of other cases where you're not necessarily running the FE study, but maybe just utilizing interpolation and running a lot of different studies, which is nice. And there's a lot of kind of power here under the hood. Great. So let's hop back to our slide deck here. And let's kind of spend the last bit of time talking about Multiscale Designer. So Multiscale Designer is a great simulation tool for the development of predictive material models. We just went over talking about how some of the other tools from our suite can benefit you. Multiscale Designer can be very advantageous for accurate material modeling, specifically for heterogeneous materials. So if you're unfamiliar with what a heterogeneous material is, I'll just give an example, just say a carbon fiber composite. So it's anisotropic, meaning that the material values for strength are different based on the orientation of the system. Specifically, what Multiscale Designer does is it can actually characterize the fiber and the matrix, which we'll talk about, why this is so important in the next slide. So really, in a nutshell, Multiscale Designer is creating a more accurate material model. It can build, whatever kind of lattice or material card you want. So pretty much runs the gamut in terms of infinite possibilities in terms of setup. And the cool thing about it is it can build those material cards for, again, our Altair solvers. But if you're using an external solver, it works with all the external solvers as well. So it builds a material card and gives you a much more accurate representation of a heterogeneous material model. So let's kind of talk about this a little bit more. I'm sure this might be foreign to some of you. Multiscale modeling is relatively new, within the past few decades or so. That one of the classical ways, so if we think about a heterogeneous material, and I'm just going to talk about it from a composite perspective, I'll talk about a couple other use cases in kind of a subsequent slide. The composites have anisotropic or orthotropic behavior. Classically, how you would kind of set up a composite model is you build up your plies, and each ply would have an orthotropic material property. But one of the things in that individual ply across the X, Y, and Z direction, you'd have different values in the X, Y, and Z. That's what an orthotropic property is. But it's not factoring in kind of the fiber and the matrix orientation. So if you actually look at kind of the microstructure here, it's not necessarily, it's not a uniform X, Y, Z, like this is what your Young's modulus is going to be in the X and the Y and the Z. It's really kind of very different, and material scientists have been aware of this. So one of the things that, if you're doing composite design and doing composite structural analysis, the classical approach was you'd always have to kind of iterate and make sure your FEA results matched experimental solving. So it could be kind of I don't want to say tedious, but maybe more labor intensive. What Multiscale Designer is actually doing is it's actually looking at the individual scale, the unit cell at the fiber and matrix, and homogeneizing those properties to give a much more realistic perspective of the orthotropic properties. So what you do in Multiscale is you kind of set everything up at the fiber and matrix level, and then it spits out a material card that you can feed into a composite analysis. So this is actually going to save you time when you're running structural analysis and give you a much more, I don't want to say accurate, but it's definitely going to get you a more efficient kind of modeling approach and more realistic to your material. So the use cases here, like I mentioned, I've been talking about composites. That's a real prominent case, unidirectional and weaves for composites. But the other thing, I'm sure some of you probably deal in injection molding. If you've ever tried to take fiber orientation and then run a structural analysis and apply anisotropic properties, you probably know that the fiber orientation is not uniform. It varies. It's not necessarily, everything is this strength value in the X and the Y and the Z. So there's another good use case here is you can kind of create a more accurate material representation of that fiber. Then also looking at lattice structures with the use of additive. So all these use cases could potentially be modeled for this clutch pedal right here. Clutch pedals can be carbon composite. They can be injection molded, or even start looking at some additive manufactured lattice. So by having a much more accurate material representation, when analysts or designers are actually running simulation, they can be confident that their results are going to meet the structural requirements. Long story short, you're going to have a much more accurate simulation. You're going to have less time spent building physical prototypes. You see how all these feed, the two solvers it's showing here is OptiStruct and Radius, but like I said, we interface with other solvers as well. All right, so let's jump into an example here. I will hop out of here and let's jump into Multiscale here. All right, so Multiscale, how it functions, like I said, is you're building pretty much that unit cell lattice, and you're building kind of that material card to be fed into a structural analysis. It's giving a much, and again, this is kind of the tip of the iceberg. You probably spend a lot more time talking about Multiscale and all the tools I've talked about today, but let's kind of run through an example and kind of show you the GUI. All right, so first things first, let's move this here. I'm just going to name this as a webinar. Hit OK. And I will create a unit cell model. So you'll see right here, if you remember my one slide, it's kind of creating the fiber and also the matrix here. So you'll see right here, I can specify, in this case, this is my fiber, what type of model it's going to utilize, whether it's a lattice, a woven particle, a core. So like I said, there's a lot of applications within this tool. I'm going to say my fiber volume fraction is going to be 30%. And what it'll actually do is it will kind of create how it's going to mesh the individual elements and how the material card is going to be applied. That's what you see right here, the meshing control that's being applied. I'm just going to specify just an adaptive setting, so it's going to automatically kind of create that mesh for me. So what you'll see if I hit run, does this pretty quick. And so let's visualize what exactly I'm talking about. So if I go to visualize here, you'll see that it's creating the fiber and the matrix. And it's doing that through kind of creating these individual elements. And what we'll see next, because I'm actually going to apply the actual materials, it's going to give the materials and homogenize them to kind of make an accurate perspective of the material for each individual element here. So it's kind of doing all the work in the background for you of building the material card and giving a much more accurate representation, for, in this case, a carbon composite, but it could be for an injection molded model or what have you. I could even open up HyperWorks now and you can kind of see the direct elements it creates. I'll do it real quick just to show you. But bear in mind, you can also do this with already a pre-established hypermesh model or Radius or OptiStruct model, where you have the mesh built and you're just trying to get a much more accurate material card. So the input would be the mesh you already have and then building the material data accordingly. And just waiting for it to load real quick. And And let me just turn on the results so you can see the mesh better. So yeah, you kind of see right here. Note, I haven't defined any of the materials yet, but it kind of gives you an understanding of how it's going to kind of build out the system. So the fiber and the matrix. So kind of relating things back to what you're seeing here, you kind of have your fiber and your matrix set up. All right, so let's go through our next step here. Okay. All right, so we've built our unit cell. So this is how, when I say unit cell, this is how our orientation of our fiber matrix is going to be set up. We now need to key in our materials for both the matrix and the fiber. So we come over here and key in our material values. So in this case, it's homogeneizing all these properties. It's putting across each of these elements. So it's the classic way of doing this is you wouldn't create this unit cell and you just have orthotropic properties or for your composite. In this case, it's kind of doing all that for you in the background. All right, so we'll start with the matrix. All right. Oops. And note, I'm doing this for isotropic, but like I said, this is the tip of the iceberg. You do this for truly anisotropic. Even across the matrix, you could have a lot of different kind of values in terms of what you're keying in here. All right, great. And then if I go to the second, so the matrix and the fiber. So relating again, so here's your matrix and your fiber, kind of these little square shapes here. We can key these in. Okay, great. You can also specify the different type of material type, what you're kind of referring to. In this case, I kind of want to create orthotropic materials for structural analysis and OptiStruct. So what I can do is I can hit run. It's going to take these values and apply them to the fiber and the matrix. And what you'll see from the actual result here is you'll see that you'll have the material orientation specified, but you'll see in the actual Excel file right here, in both tension and compression, we have the material matrix set up. So this is actually fed as a card data into OptiStruct or Radius or whatever solver you have. And then you could even, if you wanted to run a simple test case, you could kind of visualize the results, via Hyper-View if you wanted to. Great. If I wanted to do nonlinear material characterization, where you actually have bilinear damage, multiple material models here, you could do that as well. So, really getting into kind of some of you composite guys are kind of concerned with having a much more accurate material model built into the tool versus what you classically have had to key in whatever FEA tool you're working in. Okay, great. Let me hop back into my slide deck here. Yeah, so we're almost at the end of this. One of the key things I want you to keep in mind, if you do have any questions about anything, let us know. I'll take some time now to respond to some questions since we're at the end of this webinar, but keep an eye out for our blogs and our YouTube page. Specifically, the other thing, we typically run a webinar every month. So we have another webinar coming up next month, so keep an eye out for that. And like I said, thank you so much for attending, and hopefully this gave you some more exposure into some of the unsung tools within the Altair suite. So I'm going to take some time now and respond to some questions. Okay, so one question here on MotionSolve. If you create your joint in CAD, do they translate in MotionSolve? It depends on what CAD tool you're using and the metadata that gets brought over. For the most part, you're going to have to redefine those joints depending on what your tool is. There is ways of doing it, but you're going to probably have to redefine those values in our environment. But it tends to be a lot easier because you're not because you're using compliant joints, and most CAD joints are not compliant. That's why if you try to add too many mates or joints in CAD, you can over constrain something. So yeah, you'll have to probably most likely redefine them in MotionSolve. Good question. Oh, good question here. So the question was, is there a difference in hardware requirements for HyperStudy with standard FEA? Is it CPU or a GPU-driven solver? So HyperStudy is actually an automation platform. So depending on the solver you're utilizing, you can take advantage of CPU or GPU. So all of our, I'm just going to talk about, within the Altair space, all of our solvers are CPU or GPU driven. Depending on what units you have available, David, you should be able to do that. As far as what HyperStudy is utilizing within the interface, it's powered by both, but it ultimately depends on what you're doing. If it's using a solver, say you're using something that's very GPU heavy, like radios or something else, yeah, I can take advantage of that. So it's kind of executing the tasks and running it in the background. Good question. And I think your other question in terms of hardware requirements, I can send you a list if you're curious about that. Just for your reference, I was just running everything today on a 6-core machine. It just depends on how long you're going to take to run, David. You don't need to have a super machine to utilize HyperStudy. It's just what your expectations are for output or timing. So yeah, there is a minimum requirements list I can send you, but you don't need to have a super machine to utilize the tool. I think that answered your question, right? Right, David? Okay, great. Thanks for the question. Sure, John. Yeah, we can work on getting those minimum requirements sent out. Any other questions on anything? I'll stick it around the chat a few more minutes if anybody else has any other questions. But if you don't have any other questions, feel free to exit the webinar. Thank you so much for tuning in today. But like I said, I'll stick around for a few more minutes if anybody has any further questions.